Okay, I want to look back at number 2 and number 4 from the double polar integral problems and show you where I made some fatal mistakes that probably made them a little bit more complicated than they needed to be. Number 2 is the first one. The mistake that I made here is that when I was copying the problem, I took the boundary, the x squared plus y squared equals 2 from problem 2, and then tried to apply it to the roof from number 1. So let's go back and look at this from the point of view of just doing problem number 2. Okay, so the roof in this problem we saw was z equals x squared plus y squared, which we said is going to look like this. It's going to start here at 0. It's going to make its way up as a parabola in all 4 directions and kind of give you a bowl type shape. And then what we did is we said the boundary and the floor was this, let's go back and take a look, get it right. X squared plus y squared equals 2x. X, there we go. Oops, sorry. Which we played around with using completing the square. Is going to give me x, minus 1 squared plus y squared is equal to 1, which meant that this in 2 dimensions is this guy, right? And that's going to be like this guy. So we were talking about like putting that surface kind of on here. And we're talking about the region that lays between these, and the assumption is this should be a positive value, and we kept getting negatives. And it was because we stopped using this as the ceiling and started using the one from problem 1. That's not going to work. All right, so let's carry on from there. The next thing we did is we looked at this and said, well, how can I write that as a polar? And we said, okay, if I have x squared plus y squared is 2x, then this is r squared, and this is 2r cosine theta. We divided out the r's, and that we got that r is 2 cosine theta, and then we played around with the theta and saw that the domain had to go between 0 and pi to do one complete rotation on this circle. So that set us up with our integral, right? Our integral had to have the r dr d theta. The theta had to go from 0 to pi, and the r had to go from 0 to 2 cosine theta. And the inside should have been x squared plus y squared, right? In that terms, right? X squared plus y squared should have been my interior, right? And we needed that because that's given in the problem as x squared plus y squared is z, so that's my interior. All right, so this we know is just r squared, so that's this, which gave me the nice neat integral 0 to pi 0 to 2 cosine theta r cubed because of the other r. Oops, let's make that r cubed because of the other r, dr d theta. Okay, so taking the antiderivative is going to give me 1/4 r to the 4th from 0 to 2 cosine theta. There should be a theta there. D theta, and then doing the substitution is going to give me 0 to pi 1/4. 2 to the 4th is 16 cosine to the 4th theta d theta. Okay, so moving from there. We can do a little bit of simplifying here. 0 to pi, 4 goes into 16 4 times, cosine to the fourth theta d theta. And this is where we had introduced this thing, which I wrongly did go me, but the double angle formula should be that. So let's think about what's going on here. This is the same as cosine squared theta squared d theta, which is going to give me now 1/2 plus 1/2 cosine 2 theta squared d theta, and then we get the nasty expansion. 0 to pi, 0 to pi. So this is going to be fourth, that's going to be a quarter. Half times a half is a quarter times 2 is back to a half. Cosine 2 theta plus square that, it gives me a quarter. Cosine squared 2 theta d theta is the result of the expansion. And this is all multiplied by 4, so let's distribute, which is going to give me 1 plus 2 cosine 2 theta plus cosine squared 2 theta d theta. And because I have the squared here, I have to apply the trig identity once more, which gets me 0 to pi, 1 plus 2 cosine 2 theta plus a half plus 1/2 cosine, and now we're going to multiply this by 2 again, so we're going to get 4 theta d theta. Okay, so I can do some simplifying here. It gives me 0 to pi, 3/2 plus 2 cosine 2 theta plus half cosine 4 theta d theta. Okay, so now we take the antiderivatives. It's going to be 3/2 theta. Because of the use substitution here, I'm just going to get not cosine. Cosine goes to sine 2 theta. And this is going to divide by 4, so that's 1/8 sine 4 theta from 0 to pi. Now, this is where some interesting stuff happens. When you're on the positives, you're going to get 3/2 theta plus sine of 2 pi plus 1/8 sine of 4 pi. And then you're going to subtract from that 0 plus sine of 0 plus 1/8 sine of 0, which fantastically, that's 0, that's 0, that's 0, that's 0. So the whole thing is 3 pi over 2. And that's our final answer. Now, let's play around and see if that jives with what MATLAB would give us. So yesterday you watched a video on using MATLAB for this purpose, right? So we can kind of crash everything together here. We're going to create a function handle f, right, at tr, and I'm going to make t the variable for the theta. And my function, though, is what's on the inside, which is just r cubed, right? So that made a function handle. I need a g, which is going to be a function of theta alone, which is going to be that 2 times cosine theta. Right, so I get the f and the g, and we're going to take an integral 2 of f from 0 to pi, and then from 0 to g, right? So the outside bound is 0 to pi, the inside bound is 0 to g, and that gives me this 4.7124, and if I happen to take 3 times pi and then divide that by 2, I get the same value. So MATLAB and my work by hand seem to be in agreement now for this problem. All right, so that should handle number 2. So it was not as bad as I was making it out. This is why you don't do math in public, because you make errors and you have to fix those. So let's now maybe, what can I do? I can start down here for number 4. I think I get enough space. So looking at problem number 4. All right, so that problem said take this and then find the polar version of it and then solve, right? So let's take a look at that guy. So the integral in that problem is the integral from 0 to 1 of the integral from y to root 2 minus y squared of x plus y dx dy. Okay, so here's my fundamental flaws in this one. All right, I was good with these being y bounds, 0 and 1 being the y bounds here. I also, but here's where I made the mistake. This is an x reality. So this is x equals y, which is fine. That's still this guy, right? So this is still x equals y. But I got the wrong part of the circle here, because this is x is equal to square root of 2 minus y squared, which means that I have x squared plus y squared is equal to 2. So I was correct in the idea that I had a circle whose radius was square root of 2. However, where I made the mistake was thinking, oh, this is a function of y is a function of x, which would give me the circle this way. But this is x is a function of y, which is going to give me the circle this way. So what I need to look at here is radical 2 this way, radical 2 this way, negative radical 2 down here. And the part of the circle that I'm looking at here happens to be this one. Okay, and I'm going, x is ranging from x equals y to that circle. And this point, if I look, okay, so the question is like, how do I know that these cross here, right? So y has to equal the square root of 2 minus y squared, which means y squared has to equal 2 minus y squared, which means 2y squared has to equal 2, y squared has to equal 1, which means that y, this is going to cross here, and if I had the other part of the circle, it would cross down here at negative 1. So this is the point 1, 1, where these are crossing. So I'm between 0 and 1 here, and I am between y and radical 2 minus y squared here. So this is the region in the floor. All right, so let's look at how do we articulate that in polars, right? So if this is x equals y, this should be where theta is pi over 4, right? That's halfway between there and pi over 2. And this is when theta is 0. So my integral should have a theta from 0 to pi over 4. And then on the inside, I should be running from 0 to a circle with a radius of root 2. So that's just 0 to root 2. And then I have x plus y, which is r cosine theta, plus r sine theta. And remember, it's r dr d theta. Okay, so now I have the integral. Okay, so let's look at how this works. This is going to go 0 to pi over 4. 0 to radical 2. I'm going to factor out the r and bring this r in, so that's going to give r squared cosine theta plus sine theta dr d theta. Okay, so this is all just a constant at this point. So I'm only dealing with the r. So this is 0 to pi over 4, that should be. 1/3 r cubed times cosine theta plus sine theta from 0 to root 2 d theta. Okay, so let's see. This is going to go 0 to pi over 4. root 2 cubed is 2 root 2 over 3. 0 cubed is 0, so this just becomes this. d theta. Okay. So now we have to work the thetas. So this is now a constant, and this is working. So I'm going to get 2 root 2 over 3 times cosine goes to sine theta. Sine goes to negative cosine theta from 0 to pi over 4. So this is 2 root 2 over 3 times, let's see, the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is root 2 over 2. The sine of 0 is 0. The cosine of 0 is negative 1, or is positive 1, minus positive 1, right? So this goes to 0, this goes to 1, so this just works out to 2 root 2 over 3. So this is number 4, right? And again, I can kind of verify my work using MATLAB. This would be a fun one to work kind of both ways, but let's clear it all out. If I put in f is a function of theta and r, where r is r squared, right, cosine theta plus sine theta, right, I think is our guy. No, it's yeah, x is r, yeah, r squared cosine theta times sine theta, right? And then, whoop, it wants a times there. Times. There we go. Now, I'm not so good with the typing today. Times. There it is. Okay, so let's make a g. G has to be at y. Let's make a g1. Right? Yeah, g1 has to be at t. Oh, g. No, these are all constants. I don't need a g. So I can just do integral 2 of f from, so the theta is going to go from 0 to pi over 4. The r is running from 0 to square root 2, right? And that gives me that, which 2 times square root 2 divide by 3, I need a dot there, I think. All right, is the exact same value. So MATLAB agrees with our work by hand here. So there you go. That should solve problems 2 and 4 from the polars and give you something to work for. Thank you.